Text-to-image diffusion models generate images by gradually cleaning white Gaussian noise to a naturally looking image, conditioned to visually match a descriptive text prompt. Latent diffusion models work in a similar way, but instead of denoising images directly, they denoise a compact latent representation which is later decoded into an image. In this work, we explore latent diffusion models. However, to keep the explanation clear and for visualization purpose, we only present our experiments directly in the image domain. The ability to generate many different images from the same noise comes from its whiteness. White noise has equal energy across all frequencies, meaning it carries no built-in bias toward any specific type of structure. In this work, we investigate how different frequency components of latent white Gaussian noise influence the visual attributes of the decoded image. Our hypothesis is that although all frequencies have similar strength in the noise space, they play distinct and unique roles in the final decoded image. In this figure, we generate images by mixing low, mid, and high frequency components from different noise latents. Our analysis shows that when we separate the noise into low, mid, and high frequencies, each group plays a distinct role in shaping the image. Low frequencies control the overall structure and color composition, which is why each row, sharing the same low frequencies, produces images with a similar global appearance. Mid and high frequencies add finer details, as seen in the variations within each row across the left and right figures. The next part of our analysis asks a natural question. Can we manipulate the frequencies of the noise to steer the generated image towards specific visual information? This is a non-trivial problem. Even if certain frequencies are linked to particular visual attributes, altering them can easily disrupt the noise distribution, making it unsuitable as an input for diffusion models. We bias the latent noise by injecting high, mid, and low frequency components taken directly from the reference image into the corresponding frequency bands of the noise. As we can see, injecting only high frequencies produces an image with no resemblance to the reference natural image, while injecting mid frequencies leads the model to generate a flat gray result. Surprisingly, when we inject low frequencies, while normalizing them to preserve the noise distribution, the model generates an image that closely resembles the natural reference and shares its color scheme. The low-frequency structure is preserved, but a closer look reveals different high-frequency details. To this end, we introduce colorful noise, a simple training-free method that conditions the latent noise toward the structure and color layout of a guiding image. The idea is simple. We first transform both the image and the noise into the frequency domain using the discrete Fourier transform. We then replace the low-frequency components of the white Gaussian noise with normalized low-frequency information from the guidance image and invert the signal back to pixel space. The resulting noisy image, which we call colorful noise, is then used as input to the diffusion process without changing anything else. As we can see, the resulting image aligns with both the text prompt and the color scheme and structure of the reference image. In addition, since we're only guiding the low-frequency information, the prompt can be changed freely. For example, we could replace the scene with corals or with colorful parrots flying in the sky. Colorful noise can also be applied with a masked input, where only the painted regions are spatially replaced in the white Gaussian noise latent. In this example, we start with a simple sketch of a cat along with its mask and use it as input to the diffusion model. As can be seen, the masked image enables flexible generation of the cat across different locations and styles, while still preserving the guidance from the original condition image. Beyond this, the flexibility of the method also allows us to generate other subjects, such as dogs, a wolf, or even a moose. Thank you for watching. We invite you to read our paper to learn more about colorful noise, including additional details and exciting applications, such as color-preserving image stylization and stylistic color interpolation.